NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Good evening, folks, wherever you may be. I am Brian White from JPL's Office of Communications and Education, and welcome to the Von Karman series, our first talk of 2022. This is an opportunity for us to engage in the public. Now, this is your space program, so if we have any technical difficulties, we ask for your patience. JPL is great at landing on Mars, but sometimes I personally have trouble with my Wi-Fi. Tonight, we'll be discussing SWOT, surface water and ocean topography, the first mission that is specifically designed to measure lakes, reservoirs, wetlands, and rivers. It will also observe the oceans and benefits from a 30-year legacy of ocean observing satellites. Joining us this evening is our questions co-host, Jocelyn Argueta. Hi, Jocelyn.
Hi, Brian. It's great to be here tonight. And I just want to remind everyone that's watching that as this is your space program, we want you involved in the conversation. So please add your questions to the chat throughout the discussion, and our amazing social media team will get those to us. We'll try to answer as many as we can. And if you can't see the chat, just hit refresh and it should pop up.
Thank you very much, Jocelyn. Now, our speaker tonight serves as the supervisor of the Water and Ecosystems Group at the Jet Propulsion Laboratory. He has worked at JPL since 2014. His research interests relate to Earth's water cycle, and he never misses an opportunity to swim in an ocean, lake, river, or cave, no matter how cold. Please welcome Dr. Cedric David. Hi, Cedric.
Hi, Brian. Hi, Jocelyn, and hi, everyone out there on the interwebs. Real pleasure to be here. Thank you so much for having me. It's an honor.
It's so wonderful to have you with us today. Let's just start off easy. Who are you? What do you do?
Well, Brian, that's a great place to start. So who am I? I am just an ordinary guy who happens to be a scientist, an immigrant, and just someone who really cares about water. So I grew up on the Mediterranean coast of France in a city called Marseille. And I moved to the United States about 17 years ago for graduate school. Ended up moving to Los Angeles about 7 years ago. And maybe we can start by showing image number 1, please. Yeah, so I really like these two images. The one on the left is my hometown as seen from the International Space Station. This is Marseille, France. And then on the right-hand side is Los Angeles, where I live now, as seen from the Terra satellite. And what's pretty great about these two pictures is you can see a lot of geographic similarities between these two places that I've called home at different parts of my life. And, you know, from above, it all looks just the same. And they also happen to have very similar climates. So now, you know, as far as what do, I am a hydrologist, which means I study the Earth's water cycle. And specifically, I like to look at rivers, but also other things like lakes and reservoirs. So overall surface waters. And perhaps we could show image number 2, please. Yeah, so this is an animation of some of the work that I do. I spent some time simulating how water moves down river systems throughout the world, a mix of equations and observations, whether it be from observations on the ground or observations from space. And so what you're looking at here is the thickness of the blue lines varies as a function of how water is propagating from upstream to downstream. And we're looking at the Mississippi River Basin, which is the largest river basin in the United States. It covers about 1/3 of the United States in area. Now, one thing that I find really special about these animations is that they give you an indication that, you know, the Earth is a living planet, and perhaps water is flowing through the continental arteries. And but so overall, yes, I'm a hydrologist and I study surface water.
We're talking about surface water. Why is surface water important?
I think that's a great place to start. And perhaps we should state the obvious. first, Brian. So water is essential to life. And as a matter of fact, when NASA looks for life in other worlds, one of the first things that we look for is the presence of water or the potential for water. Now, of course, water is also essential for us on Earth, for humans, but also for ecosystems. And perhaps we could bring up image number 3, please. So I really like this image. We can start on the left-hand side. This is the blue marble as seen by Apollo 17 in the early 1970s. So the first thing that you notice is that this is the blue planet, right? And of course it's blue because we have lots of water, and that makes our planet very special compared to other places in the universe. Now, the blue planet also has a lot of white, and the white turns out to be water as well, whether it be clouds or ice caps. In this particular case, the Antarctic, the ice caps in Antarctica here in the southern pole. And so lots of water, blue water and white water. Now, if you take all of the water of the earth, water in the oceans, in lakes, reservoirs, groundwater, water in people, in trees, in animals, and you put it all in a big sphere, you end up with the big sphere that is on the right-hand side here, just above the state of Utah. So this is an image that was produced by our colleagues at the U.S. Geological Survey, which I think is very powerful. So, it might seem when you look on the left-hand side that we have tons of water, but when you put it all together, maybe not as much as we might have thought. So this big sphere here is all of the water on Earth, right? But the vast majority of it is salty. That makes it kind of not great when you try to drink it, and it's not perfect if you try to irrigate crops either. So another way to look at it is if you take away all the oceans and seas and you take away another notable portion, which is frozen water, same thing, not the best to drink. Now you end up with that little bubble to the right of the big sphere, and the bubble that is just above the state of Kentucky. Now this is liquid fresh water, so not the salty, just fresh water, and not frozen, all liquid. So little smaller of a bubble. And now the vast majority of this little bubble is actually groundwater. Now groundwater is great because it helps us in times of needs. If it gets pretty dry, in case of a drought, it is a nice source of water, but you do have to go pump it. So you got to go extract it from the ground, and that takes effort and energy. The other inconvenience with the groundwater is that it takes hundreds of years to replenish. So that means when you take it away, then it's likely not going to come back anytime soon. And we've seen from a variety of other NASA satellites that basically groundwater has been depleting around the world. And so you can think of groundwater as a savings account for water. And we've been withdrawing quite a bit from the savings account, which can be concerning. Now, if you pay attention, just underneath that little bubble is a tiny pinpoint dot, a blue dot just above the state of Georgia. Now, this is all of the liquid fresh water that is within Earth's rivers, lakes, and reservoirs. So now what makes this tiny dot very special is that the water in Earth's rivers, lakes, and reservoirs is the most renewable and the most accessible source of fresh water. And so that also, because these two together, it makes it the most sustainable source of fresh water. And this tiny dot is also special for us humans because most of the ancient human civilizations were born in great river valleys. And so, the proximity to this easily accessible and renewable source of fresh water has been an important factor in basically the birth of humanity. But so one thing to remember here is that, that's basically all the water we got. All right. And it might change from, one bubble to the next, depending on the evolution of the water cycle. But that's all we got. And another thing that I think is important to look at is how many people we are. And perhaps we could bring up image number 6. Image number 6, please. So yeah, this is a chart that shows the variation of the growth of human population starting 10,000 before Common Era to now. Brian, did you want to say something? Yeah. Okay. All right. What you can see is that there's a big rise in population. Right. We started with basically nobody, and it's been rising very quickly up to now. So for reference, in 1800, it was just about 1 billion human beings on Earth, and right now in 2021, almost 7 billion human beings on Earth. Almost 8 billion, actually, over 7 billion. So that's billion with a B. And so we only have this much water, and the human population has been growing very rapidly. And so what this tells you is that the amount of water per person has been decreasing, which can be concerning. Now there is another portion of the story, and if you don't mind, would you please bring up image number 7? Yeah, so rivers don't care about political boundaries, right? So rivers flow across national borders, and water is also a shared resource. So what we're looking at here is a map of the world, and those polygons here in green, yellowish colors are what's called river basins. Right? And a river basin is basically an area where if it rains there, the surface water is only going to stay within this polygon, and it will flow eventually all the way downstream to the nearby ocean. And so now the river basins that we're showing here are all of the world's river basins that happen to touch multiple countries. All right, so surface water is a shared resource, and what's important to recognize is that, of course, water is vital for everyone. Now, if you're lucky and you happen to be living upstream of one of these river basins, basically you have first dibs. First dibs on the water. All right, so that's great. Lucky you. And water is vital for you. I get it. But if you happen to be living downstream of a river basin and perhaps somebody else grabbed it before you had access to it, then it could become a problem. So, water is vital. It's a sensitive resource because it's shared across nations. And again, there is only so much of it. So an old adage is you can't manage what you don't measure, right? And so we have to manage this precious resource. And perhaps we could bring up image number 4, please. All right, so this is how we've been measuring surface waters around the Earth. Basically, you put a stick in the water or maybe a ruler, and you measure how high the water is. If you add to that little knowledge of how deep the water body is, the shape of the bottom of the water body, what we call bathymetry, and some physical equations of hydraulics, then you are able to determine how much water you have and perhaps even how fast water is flowing, which is, it's pretty great. So, the old school way is to use a ruler like the image on the left. A more modern way is to use a radar, perhaps mounted on a bridge just above a water body. And then the radar will shoot a radar signal straight down, and that signal bounces on the water, comes back, and by measuring the distance between the radar and by measuring the time that it takes for the signal to come back, we know how high the water is. And that little antenna that is at the top allows you to share the data on the internet. So that's pretty cool. Now, there's a problem there. And if you could bring up image number 5, please. So this is a map of where river gauges, so like the ones that we just discussed, are located around the world. And so all the dots here, whether they're dark or light blue, are a place where at some point there was a gauge, a river gauge in the world's rivers and lakes. Now, first thing you notice is that in some places there just never has been one. Okay, so that could be an issue. The other thing to note here is that those gauges that are light blue basically have not been accessible. Data has not been accessible since the year 2000, either because the people taking the measurements are not sharing them, or because they're just not paying for the measurement at all. And those gauges, which are darker blue, are gauges that are still available past the year 2000. And so what we're learning from this map is that river gauges are disappearing. So let me summarize the whole story for you. We only have this much water. And then we have so many more people than we've had in history, and that's growing and growing. Surface water is a very precious resource that is shared across nations. And now we're realizing that the measurements that we need to properly manage the precious resource are going away. And that is a problem.
I love how you very succinctly kind of are able to just talk about that, of this is what we need to be monitoring. So what I want to then ask is, what is SWOT, and how is SWOT going to help with this, and why should we all be talking about this too?
Thanks, Brian. That's a very good question. So, what is NASA doing about this? And so maybe, if you don't mind, would you bring up picture number 8? So we have a plan. That plan is called the Surface Water and Ocean Topography Mission, of which we're only seeing the instrument here. So this is a picture that was taken about 6 months ago in one of the clean rooms at the Jet Propulsion Laboratory. So this is the main instrument on a mission that has been in development for over 15 years. It's a joint effort by NASA and by the French Space Agency, CNES, with contributions from the UK and Canadian space agencies. And so, there's a little bit of a personal thing here for me. Is it's been primarily developed by the country where I was born and the country where I live and work and have done so for many years now. So very special mission. But let's talk about what it's going to do exactly. And if you don't mind, would you please bring up image number 9? So here it is, an animation of what SWOT will do. So this is something that exists for real, right? The animation, the picture that I just showed you is the instrument that will be built. It's just the instrument. We shipped it to France so that they put it on a spacecraft and then ship it back to us, and we're hoping to launch it. The plan is to launch it at the end of the year, end of 2022. So it's happening this year. It's super exciting. So this is a satellite that will be at about 800 or 900 kilometers in altitude above the ground, and will orbit around the Earth every 21 days, approximately 21 days, repeat its cycle every 21 days. Now, on the spacecraft is a radar that is specifically tailored using a frequency so that when the signal that is being sent from the spacecraft hits the ground, it bounces if it happens to be water, and not so much if it's not water. So that allows us to map where water is, which is pretty cool. And now by measuring the time that it takes for the signal to do a round trip between the spacecraft and the ground, we're able to estimate how high the water is. Now, this is great for 2 reasons. So the mission is going to do 2 things, as you said, Brian, in your introduction. A portion of it is ocean topography. And we've been doing ocean topography for over 30 years at NASA. And so basically measuring the top of the ocean allows us to measure things like sea level rise. And so this mission is going to keep the legacy of these measurements. But what's transformative about the measurements above the ocean here is that we will be able to get a much better understanding of ocean circulation globally. So we won't be talking too much about the oceans today because that's not my expertise. But perhaps let's spend some time looking at what it means for surface water. So of course we're flying above the state of Florida here, and you'll notice that when the radar signal hits some of the surface water body, we detect them. And so knowing where they are and how high the water bodies are in a way that is very similar to those local ground gauges that we discussed earlier, will be able to determine the variability in how much water is being stored within surface water. And again, remember, this is the most renewable and most accessible source of fresh water. So we'll be able to monitor that And then by combining things like the width of rivers and the height and slopes, we'll be able to also get a pretty good estimate of how fast water is flowing and how much water is flowing through river systems. Now, what's really exciting is that this is a global mission, right? I mean, we fly spacecraft above the entire Earth and all continents, and the data will be easily accessible and freely accessible to anyone on this planet, which means that all the data that we haven't had or that has disappeared is now coming back. Now, of course, you can't make a direct comparison between space measurements and some of the measurements that we would be taking from the ground, but this is going to be a great ally to a lot of the in situ measuring networks that we've had, acknowledging that a lot of these have been going away. So a true transformation for hydrology and for understanding of the Earth system, and great potential for helping with water management throughout the world.
That's very cool. I imagine a question we're getting in the chat, and we'll get to those really shortly, is how is this different than other missions that we have out there?
Well, that's a great question, Brian. And so perhaps some folks in the audience might be familiar with Landsat images, the kind of thing that you would see on Google Maps, for example. Now, these are basically cameras like the one you might have on your phone that are on a spacecraft and that are taking pictures of the ground, visible images of the ground. Now, if you'd like to see where water is, and I'll focus my answer on the continents here, Brian, because that's my expertise. But so if you'd like to know where water is with those images from, basically what's a camera on a satellite, well, it has to be during the day, right? Now, 50% of the time, it's not the day. It is what it is. And now, if you happen to have a cloud in front of you, then you can't see the rivers and the lakes. And you might recall from that blue marble picture earlier that we have lots of clouds on the Earth. About 70% of the Earth is covered by clouds. And so, 50% of the time it's night, 70% of the space you have clouds. And now the beauty of the radar measurements that we're using here is that it doesn't care for day or night, doesn't care for clouds. It's just going to go through and be able to measure any time that it flies above an area of interest. So that's something that's really special. Now, another portion, and if you wouldn't mind animating this video again. So we have a history of knowing where rivers are, right? And where lakes are. Now, we also have a history of measuring ocean topography. That's what we were talking about earlier. But the vast majority of the missions that we've had for 30 years have only measured directly underneath the spacecraft. And you might see a little red dot that goes up and down between the satellite and the ground here. And now that basically only measures the line that is directly under the spacecraft and not the swaths that you see further away from it. And so the measurements that this new mission will provide basically will give us images of not only where the water is, but how high the water is. And now the problem with those lines from historical traditional missions is that they may or may not cross a water body on continents. And if they don't, then basically you're out of luck. Now, what SWOT will do is it will basically touch every one of these water bodies with its images. And so makes it a really transformative mission.
That's wonderful. When I think about this, and a lot of times when people think of NASA, they think of looking out, they think of looking up. They don't necessarily think of looking back. Can you talk a little bit more about that?
Yeah, what's up with that? I agree, and Brian, I feel the same. When I meet people, talk to friends, and say I happen to work at the Jet Propulsion Laboratory, the first thing that people bring up would be the Mars rovers, or the Mars helicopter, or the Voyager spacecrafts that have left the solar system. People think of telescopes, particularly these days, telescopes looking deep into the universe and back in time. And so, of course, NASA is interested in the exploration of the universe. Now, it just so happens that our solar system is part of that. And our home planet is Plan A, is part of the solar system. And, as far as we know, that's the only place where we can live right now. And what's great about our ability to ship satellites in orbit around the Earth and basically take Earth selfies is that they bring a global view, the big picture of very important processes happening on the Earth. And so, in our exploration of the universe and beyond, NASA has the ability to basically look back at the Earth, and we learn a tremendous amount while doing that, and that helps us take care of Plan A. We don't have a Plan B for where we're going to be, and so it's incredibly important for NASA to look back at the Earth.
That's such a deep answer with kind of the grand scheme of everything. But what I love about these talks is we get to know the people that are doing these a little bit more. And I'm curious, if you don't mind talking about it, why water is important to you personally.
Yeah, Brian, let me take a deep breath before I answer this question, and perhaps in the meantime we could bring up image number 10, please. And so, the short version of it is that water is my friend. Water has been my happy place for as long as I can remember, and the reason for that is I was born with a physical disability that affected both of my legs, and at birth, basically the forecast was most likely I was never going to walk. And so now, fortunately, after surgeries, and I'm not including any pre-surgery picture because they're not pretty to watch, but surgery and years of physical therapy and braces. The picture that you see on the top left is part of that story. So I'm lucky that I've been able to walk this earth, and I feel fortunate, and that's something that I celebrate every day. Now, to tell you the truth, walking's never been fun. Never has. It's always a little uncomfortable, and basically a constant reminder of being a little different. And the beauty of water is, from the youngest age, swimming was the place where I felt that I was just a normal kid, where I could do things like any other kid could do. And so, throughout my life, this has been a very special place for me, a place of peace. And so, of course, I'm curious about the natural environment, and I am excited to contribute to fostering sustainability on our Earth. But I have a much deeper emotional, personal connection to water as a medium that has also driven me in part of my career. But a quick summary, a mosaic of how water has been important to me throughout my life.
I'm grateful that you have shared that expertise and that passion that you have for water with us today. I know there are people out there who have some great questions for you, so let's throw it over to Jocelyn.
Yeah, there's a lot of really great questions coming in on all of our social media platforms. To kick it off, we have Luz Maria on YouTube that's asking, what models or patterns do you think SWOT will see? Can SWOT surprise us by discovering something unexpected?
Oh, wow. Hey, Luz Maria, this is such a good question. And that's part of the beauty of space exploration and space missions is there are things that we think we will see. And that's what drives the design of the vast majority of space missions. And then there are the things that you didn't know you were going to discover. So that's the unknown unknowns. And so, what I can tell you is that we're hoping to learn about how much water is flowing through the world's rivers. We're hoping to learn about the variability of storage in Earth's lakes, reservoirs, and wetlands. And hopefully this will help shed some light on the connection between, basically the same water cycle that we've been told about since middle school. Water evaporating from the oceans and precipitating on the land and flowing through the rivers. Part of it goes underground, part of it goes back to the ocean. So we're hoping to get some key nuggets of that water cycle with the mission. And of course, SWOT is going to do a whole lot about ocean circulation. But there are things like, are we going to discover maybe that tiny pinpoint is a little bigger than we thought, or maybe it's smaller. So there is a lot of TBD as to what we will discover, and that's part of what gets me so excited about the mission. That was a great question. Thanks so much.
And our next question comes from Kalai on YouTube that wants to know, how much of the Earth's surface will SWOT be able to get measurements of?
Oh, that's another great question. And so I think that the area that will be covered is nearly 100%. I mean, there are very small polygons near the equator that we may not see. And actually, perhaps it would be a good time to bring up image the animation number 12. I don't know if you have a way to speed it up a little bit and bring it closer to the end, but we will see a view of all of the Earth's oceans being covered by the measurement. And so every 21 days, we should get a full picture of the entire Earth. And in the process of doing that, there will be some overlaps between some of the measurements. And so, yeah, that's what you will see. Basically, the entire Earth will be covered by the measurements every 21 days for at least 3 years, and we hope many more. Very exciting stuff.
And our next question from Modal Mixture on YouTube asks, will the data be high resolution enough to use for reservoir management?
Oh, yes, another great question, and the answer to that is absolutely. We were talking about pixel sizes on the order of 10 to 70 meters, and so we should be able to we will be able to observe lakes and reservoirs that are at least 250 by 250 meters. So that's relatively small. We are hoping to even be able to go all the way down to observing those surface water bodies that are 100 by 100 meters. So that would be 300 by 300 feet. And so there's plenty of capability for helping surface water management in lakes and in reservoirs around the world. Now, of course, some of these water bodies already have measurements, and those measurements are great, but a lot of places do not. And so this mission will bring some truly transformative observations that we've never had before. Another great question. Yeah, YouTube.
Yeah, and looking a little bit bigger picture here, James on LinkedIn wants to know, what are some of the ways that this satellite will help us navigate something like climate change in the years ahead?
That's a very good question. Let me step back a second and acknowledge that basically rising temperatures, physically, what this allows is for the atmosphere to be able to hold more water. And what this is going to lead to, the vast majority of people think that this will lead to an intensification of the water cycle. So this might mean more extremes, more droughts, more floods. And so by measuring the flow in the Earth's rivers and lakes, we will be able to, and basically because rivers serve as an integrator, it's the great sum of everything that happens upstream. And so it's going to be a great indicator of potential variability if that we would see from space. Now, I'm saying if because the mission is planned for 3 years, and we have a history of successful missions that last for much longer than they would. But 3 years of measurements would not be enough to infer any potential long-term changes. Now, if the mission was to last 10 or 15 years, that would be pretty great, and perhaps it could shed some light on some of these processes. Thank you. That was a great question.
And we're getting a couple of questions, so I'll end with this. One from YouTube comes that says, can you tell the quality of water with SWOT?
Oh, that's such a great question. No. So the short of it is no. So this is really a water quantity mission. And so we'll be able to infer the changes in volume and the changes in storage of water and changes in how much water flows down networks. But this will not measure the color of water. Now, we do have other satellites that help us with estimating water temperature, which is very important for water quality. And other satellites, including some of the imagery satellites that I mentioned earlier. And NASA actually even has plans for next generation cameras by the end of the decade that will give us a lot of information on water quality. So there are missions that give information on water quality that could be used along with the measurements from the SWOT mission. And we absolutely ought to do that. And then we can look towards the end of the decade for even better measurements of water quality that could be used with SWOT, if SWOT is still flying, or with the next generation of SWOT mission, should we have one. Another great question.
Well, that is all the time we have. Thank you all so much for your great, wonderful questions. Please join us next month for our talk, Roving with Perseverance, Findings from 1 Year on Mars, with Jennifer Trosper and Katie Stack Morgan from the Mars 2020 team. I'd like to thank our speaker, Dr. Cedric David, for his exuberance and his expertise. I want to thank Jocelyn and everyone behind the scenes for making these talks possible, particularly this one today. And finally, a big thank you to all of you who join us each and every month. Please stay safe, stay kind, stay curious, and we'll see you in February.